Hello everybody, I'm Vishwapriya Das, a PhD Research Fellow in the Nanoscale Device Research Laboratory of Department of Electronic Systems Engineering, Indian Institute of Science, Bangalore. Today I'm here to discuss on our recent paper that was published in the Journal of Applied Physics. The title of the paper is Predictive Model for High Frequency Operation of Two-Dimensional Transistors from First Principles. The authors are myself, Vishwapriya Das, and Professor Santanu Mohapatra. I'll start the discussion with a prologue, which is basically a roadmap of the 2D electronics. Then I will come to the choice of 2D material for a typical RF or high frequency application, and then I will discuss about the need for the non-quasistatic or high frequency modeling of the 2D semiconductors, and then I will come to the radio frequency or high frequency application of 2D materials and their history. And then I will come to the main theme of the discussion, that is the modeling of the high frequency effects in a 2D semiconductor, considering a phosphorine as a prototypical example. Then I will summarize the whole discussion and I will discuss about the further research perspectives. It is well known that the introduction of 2D materials, either in conventional semiconducting phase or in any other form of exotic quantum phase, has opened up the avenues for possible CMOS technology extension. Their library contains several thousands of such materials, starting from the graphene and its derivatives, then this transition metal dichalcogenides, monoelemental Xenes, genus materials, and more and more and more. They exhibit semiconducting, insulating, semi-metallic, spintronic, topological, and numerous other phases, and their applications are also multitudinous. Here, a roadmap of this flatland electronics is provided, which started back in 2004 with the exfoliation of graphene, and then came this MOS2, then phosphorine, silicene, tellurine, etc. From the circuit perspective, it started in 2011 with the fabrication of MOS2 logic circuits, and the bloodline was continued to achieve the greatest feat in 2017 by successful implementation of a MOS2 based microprocessor. Although the journey of 2D materials started with graphene, now we have a plethora of such 2D materials. Hundreds of such atomically thin materials are available with the commercial vendors like 2D semiconductors and HQ graphene, while thousands of them have been predicted alongside using the computational exfoliation techniques. But since the introduction of any new 2D material in the process integration phase of technology development is a time-consuming and capital-intensive affair, it is therefore very important to assess their device and circuit level performance at a very early stage of technology development. Here comes the need of first principle based multi-scale models that enable basically the systematic performance evaluation of any new 2D material solely from their available crystallographic information. On the other hand, from the application perspective, although the initial applications of the 2D materials were targeted towards the digital circuits, now they are also being explored for analog or radio frequency applications. However, for a typical high frequency application, a 2D material with high carrier mobility is desired so as to obtain a high cutoff frequency. The requirement of this high cutoff, this high frequency circuit design can also be fulfilled by adopting smaller technology nodes, which for 2D materials particularly can be very challenging and therefore expensive, as because the technology of 2D materials is still at its infancy. On the other hand, the availability of high mobility 2D material is very scarce. A recent article in Physical Review Letters connotes a similar argument, inferring that the relatively high density of scatterings is what causes the universally low mobilities of these 2D semiconductors with parabolic electron dispersions. Even the low effective mass materials like phosphorine, which initially was predicted to have high carrier mobilities, was later found to possess rather disappointingly low values. In a recent article, Gademane et al. Have reported this crystal direction dependent low carrier mobility profiles of phosphorine obtained from the full band Monte Carlo simulations. Now coming to the need for non-quasistatic modeling of the 2D semiconductor based transistors. The non-quasistatic effects appear particularly at high frequencies. The existing device models of 2D materials are built upon the quasistatic approximation, which basically neglects the finite non-zero inertia of the charge carriers and thereby completely neglecting the carrier transit time from source to drain. Under this quasi-static approximation, the channel charge can respond to the variations in the input terminal voltages quasi-statically, or better to say instantaneously. But this approximation vigorously fails when the rise time or the fall time of the input signal becomes comparable to the carrier transit time from source to drain, or even when the input signal frequency becomes greater than that of half of ft. Here ft is the transistor cutoff frequency at which the modulus of the short circuit current gain falls to unity. As a result, such models which are based on the quasi-static approximations, they become applicable for circuits operating only under the half of the intrinsic cutoff frequency ft. The essence of non-quasi-static model gains attention particularly in this scenario, that is at high frequencies. An NQS model explicitly acknowledges the finite inertia of the charge carriers, and therefore all the relevant model parameters become an explicit function of time. There are two approaches for non-quasi-static modeling. First, that is the current continuity equation based model, and the second one is the relaxation time approximation technique. The continuity equation based model is purely physics based, but it is very complex for implementation in the circuit simulators. On the other hand, the RTA, or the relaxation time approximation based approach, is rather simple to implement, but it needs the calibration of extra semi-empirical parameters. Here, for high frequency modeling of the phosphorine transistor, we have first used the continuity equation based method, but due to the added complexity of the bias dependent diffusivity, as we will discuss later, we had to develop an equivalent RTA based model for SPICE implementation. Now let me briefly discuss about the high frequency applications of the 2D materials. Regarding the high frequency applications, the 2D materials, including the 2D semi-metals like graphene and the 2D semiconductors, they have a good history. Initially, graphene was thought to be the most suitable candidate owing to its high carrier mobility and high saturation velocity, but the gapless nature of the band structure of graphene gives rise to high off current and large output conductance, which further leads to compromised current and voltage gains. Later, these shortcomings of graphene were rectified by other semiconductors like the transition metal dichalcogenides and phosphorine. However, they have their own performance limitations of low carrier mobilities and higher switching delays as compared to graphene. Anyway, particularly the black phosphorus has been extensively used in the experiments regarding the high frequency applications, but all of those experiments were conducted for multilayer black phosphorus. In our model, however, we shall consider only the monolayer black phosphorus as a prototypical example of the 2D semiconductor. Now, I will discuss in detail the non-quasi-static modeling methodology for 2D channel transistors, considering phosphorine as a prototypical example. For any other 2D semiconductor, the relevant material specific parameters like band gap, effective mass, and carrier mobilities, etc. need to be extracted from the first principle based calculations. Shown here is the Packard honeycomb crystal structure of phosphorine with its first Brillouin zone. The fundamental band gap of phosphorine appears at the zone center gamma, making phosphorine a direct band gap semiconductor with a band gap of about 0.9 electron volt. Phosphorine is however well known for its highly anisotropic electronic properties arising from the high degree of anisotropy in its band structures. As shown in the color contour plots, the high anisotropy leads to the elliptic constant energy contours of the conduction and valence bands. In fact, this anisotropy is more pronounced in the valence band, making the directional hole effective masses even more contrasting than that of the electrons. In our model, the theta is the transport direction that can take any value between 0 degree to 90 degree, where 0 degree refers to the armchair direction and 90 degree refers to the zigzag direction as shown in the figure. We start developing the model with low energy K dot P Hamiltonian of phosphorine, which was first reported by Rodin et al. In this Hamiltonian H, EC and EV are the energies of the band extrema, and gamma is a first order coupling constant between the conduction and valence band, and alpha and beta are the leading order correction terms. However, close to the gamma point, the interband coupling parameters alpha, beta and gamma can be safely ignored without losing much of the physics. This leads to a simple parabolic but anisotropic energy dispersion equation of phosphorine as noted here as E plus and E minus. Here delta C and delta V are the energy differences between the Fermi level and the conduction and valence band extrema respectively, with the Fermi energy which is set to 0. Thereafter, we can obtain the expressions of the density of states using the Herring-Vogt transformation, which is further used to obtain the carrier concentrations in phosphorine. The basic MOS capacitor structure under consideration is shown here to comprise of two capacitors in series. The first one is the oxide capacitance Cox and the quantum capacitance of phosphorine CQP. Psi s is the surface potential at the oxide semiconductor interface. Then, using the potential and charge balance equations, we obtain the surface potential equation as shown here in the red box. Although an approximate analytical solution of the surface potential equation is possible, we however solve it numerically in order to obtain the surface potential profiles. Having obtained the distribution of psi s, the quantum capacitance of phosphorine can now be evaluated using the formula given here. To be noted that since we have used a conventional gate stack on top of phosphorine, the inversion charge versus surface potential profile as shown here has come up to be linear rather than being non-linear. So this linear nature of the Qi versus psi s profile readily eliminates the need for piecewise charge linearization techniques. The anisotropic character of phosphorine is also reflected in the mobility profile. We model this angle-dependent low-field electron mobility arising from the anisotropic deformation potential using the given equation mu e equal to mu e AC plus mu e ZZ by 2 plus mu e AC minus mu e ZZ by 2 into cos 2 theta. Here mu e AC is the electron mobility of phosphorine along the armchair direction and mu e ZZ is the same along the zigzag direction. We calibrate this equation against the data provided by Gatteman et al. Therefore, as obvious it is, all the relevant electrical quantities like the diffusivity, drain current, conductance, etc. become theta dependent. On the other hand, since we have explicitly used the Fermi-Dirac statistics in our calculation, we have also introduced the bias dependent character of electron diffusivity in order to ensure the zero drain current at zero drain bias voltages. The expressions of bias dependent diffusivity is given here, which is clearly different from the conventional Einstein's relationship. The bias dependent character of diffusivity further complicates the model equations. However, for zero gate bias, the expression of bias dependent electron diffusivity becomes the same as that of the Einstein's equation. The diffusivity profile as shown here reflects similar anisotropy as the gate voltage increases. Now, using the drift diffusion formalism, we can formulate the DC drain current as noted here as IDC. Quite obviously, the drain and transfer characteristics also reflect the effect of anisotropy. For example, maximum mobility along the armchair direction yields a maximum saturation current of about 19 microampere per micrometer for theta equal to 0 degree at transistor saturation, whereas the same is almost 9.5 microampere per micrometer along theta equal to 90 degree. However, the subthreshold swing remains almost theta invariant, calculated to be 72 millivolt per decade, and also the threshold voltage of the device remains theta independent since it solely depends on the density of states of the constituent material that is phosphorine. Also shown here is the FT profile with respect to theta, which resembles a similar envelope of mobility or diffusivity. The cutoff frequency Ft was calculated using the given formula, that is Ft equal to Gm by 2 pi Cgg, where Gm is the gate transconductance and Cgg is the total capacitance as seen from the gate terminal. Here are the plots of transconductance and transcapacitance profiles. The most important thing to note here is that the conductance profiles are theta variant, whereas the capacitance profiles are theta invariant. However, this is true only for DC or low frequency of operations, as will be revealed later. Now, having obtained the expression of the drain current, that equation can be generalized for any arbitrary point x inside the channel using the principle of current continuity. Thereafter, using the Ward-Dutton charge partitioning scheme, we can formulate the expressions of the terminal charges Qg, Qd and Qs as noted here. Finally, using these terminal charge equations, we can express the respective terminal currents under the time varying external bias as Igt equal to ddt of Qgt, Idt equal to Idc plus ddt of Qdt, and Ist equal to minus Idc plus ddt of Qst. Here we have considered the directions of all terminal currents to be entering into the device. For developing the non-quasistatic model, we first note that both the channel charge and current become explicit functions of time t and position x inside the channel, and they can be expressed as qi prime of x comma t equal to minus cox into vgt minus is of x comma t, and I of x comma t equal to w into minus mu into qi prime x comma t into del psi s x comma t del x plus det into del qi prime x comma t del x. Now, with the help of the current continuity equation and neglecting the generation recombination processes, we come up to this final form of the partial differential equation as noted here. Note that there is one extra term containing the time derivative of the bias dependent diffusivity that adds to the complexity of the problem. Due to this added complexity and the way it appears in the equation, we need a priori knowledge of the diffusivity profile only to solve the partial differential equation numerically. We tackle this problem by rewriting this del d del t term as del d del t equal to del vg del t into del d del vg. This del vg del t part we can easily obtain from the derivative of the input signal waveform, but the del d del vg term requires a pre-calibration. We did the same using a fifth order rational polynomial function as noted here. Anyway, once we solve this partial differential equation using the appropriate initial and boundary conditions, then we can easily get the non-quasistatic charge and current profiles using the Ward-Dutton charge partitioning scheme. One important assumption, however, that we have made here is that there is no non-quasistatic effect present at the channel ends, that is at the source and drain ends, so that the quasistatic and non-quasistatic charge profiles are same at these points. Now we come to demonstrate the large signal transient operation of the transistor biased at saturation. For large signal operation, the input signal variation is chosen to be large enough to produce nonlinear behavior. Here, a trapezoidal pulse VGT with a rise and fall time of 1 nanosecond is applied at the gate terminal, and the drain voltage VD is always kept at 1 volt to ensure the transistor saturation. Shown in the figure are the terminal current profiles for large signal operation along the different transport directions, theta equal to 0 degree, 45 degree and 90 degree. As can be interpreted at a glance, the envelopes of these current waveforms emanating from the different mobility profiles along these directions remain basically invariant of theta. By comparing the non-quasistatic current profiles with the corresponding quasistatic counterparts, one can see that the non-quasistatic profiles have more sluggish signatures than their quasistatic counterparts. To be noted here is that the unphysical sharp transitions in the quasistatic current profiles, whereas the transition in the non-quasistatic waveforms are more gradual and physical. So this is because the non-quasistatic model basically addresses this non-zero inertia of the charge carriers flowing from the source to drain. Due to the same reason, the non-quasistatic terminal currents lag behind its quasistatic counterpart. Also note here that the magnitude of the current transients are different along different transport directions owing to the different mobility values along those directions. The small signal analysis becomes particularly important for designing analog radio frequency circuits, and often their behaviors are characterized by the small signal Y parameters or admittance parameters, which are complex quantities. By relation, the Y parameters can be represented as Yxy equal to Gxy plus j omega Cxy, where capital X and capital Y are the device terminals, and G denotes the conductance part and capital C denotes the capacitance part. Although several analytical treatments for the small signal non-quasi-static models have been proposed for conventional transistors, however, in our case, the bias-dependent character of electron diffusivity actually hinders a continuity equation-based derivation of closed-form Y-parameter expressions. Therefore, we have treated the whole problem numerically. We have applied a small signal, that is small Vg, superimposed on a DC bias voltage, which is capital Vg at the gate terminal, and then we have solved the corresponding partial differential equation numerically to obtain the certain Y parameters. The profiles of Ydg and Ygg are shown here, and also their profiles have been compared against the corresponding Y parameters obtained considering constant electron diffusivities. At low frequencies, the channel inertia is negligible, and therefore the channel charge can respond to the small variations in the applied input signal quasi-statically. This situation is favorable up to a frequency ft by 2, and that is why the low frequency tails of the Y parameters necessarily remain invariant with respect to frequency. And also this low frequency values basically converge to their corresponding DC values. For example, at low frequency, the real part of Ydg, that is the transconductance Gm, converges to almost 0.07 millisiemens for theta equal to 0 degree, which is equal to its quasi-static value at saturation. On the other hand, at very high frequencies, Ydg tends to converge to 0, which means that at very high frequencies, for say frequencies greater than 100 GHz, the transistor becomes totally unresponsive to the input signal variations. However, the most important observation here is that at high frequencies, both the transconductance and the transcapacitances become theta variant, while at low frequencies only the transconductance varies with theta and capacitance becomes theta invariant. We have also performed the harmonic distortion analysis to show that only the non-quasi-static model can capture the higher order harmonics appearing at the gate current spectrum caused by the inherent nonlinear character of the semiconducting phase. To conduct the harmonic distortion analysis, a small input signal of frequency 0.25 GHz was applied at the gate terminal, ensuring the transistor saturation by Vg equal to Vd equal to 1 volt. The result is obvious, that is the higher order harmonics appear indeed at the gate current spectra at 0.5 GHz and 0.75 GHz in addition to the fundamental frequency at 0.25 GHz. But as can be seen that the quasi-static model clearly underestimates these higher order frequency components. Now coming to a different front, here we emphasize and advertise the core nature of our multiscale model, that is any non-ideal or short channel effect can be added on top of the core model to develop a full-fledged industry standard compact model. Here we demonstrate the effects of velocity saturation in particular. In general, to cater for the high cutoff frequency requirements of typical millimeter wave applications, the channel length scaling is necessary along with the high bias voltages. Therefore, the effects of velocity saturation comes into the picture. Here we have modeled the effects of velocity saturation by calibrating the famous Cauchy-Thomas equation against the reported velocity saturation data for phosphorine by Gaitamane et al. Here mu effective is the field dependent mobility, xi is the lateral electric field, xi c is the critical electric field for velocity saturation, and sigma is a fitting parameter. To be noted that xi c and sigma are material specific parameters. To incorporate the velocity saturation, we have replaced the mobility term by mu effective in the current equation, and we have also replaced xi with psi sl minus psi s0 by L. This approach is very similar to BCM 3, however it doesn't require any empirical parameter based artificial clamping of Vd at high bias voltages. Plotted here are the variations of maximum drain current and associated cutoff frequencies as functions of channel length along the armchair and zigzag directions. That the effect is more pronounced along the armchair, that is along theta equal to 0 degree, as compared to the zigzag direction due to the difference in sigma values. However, as obvious it is, due to the reduction in channel length, FT is increased up to say approximately 90 gigahertz for a channel length of 50 nanometer along the armchair direction. The YDG profiles have also been plotted in presence of the velocity saturation. Here we can see that the real part of YDG, that is the transconductance, decreases due to the mobility degradation, while the imaginary part of YDG remains almost unaltered. The NQS model is implemented in SPICE using the relaxation time approximation technique, which as shown here is in good agreement with the continuity equation based model up to a frequency of 2ft. We also perform the analog and digital circuit simulations in this case to indicate the superiority of the NQS model as compared to the quasi-static model. This is the transient response which is shown here for resistive load logic inverter. One can see that there are unphysical spikes, overshoot and undershoots as predicted by the quasi-static model, which is mostly eliminated by the non-quasi-static model. Also look at the gain frequency profile of the common source amplifier. Here the quasi-static and non-quasi-static models, both of them produce the same result for low frequency operations. However, the quasi-static model diverges at high frequencies, whereas the non-quasi-static model produces the correct results. Now to summarize everything, considering phosphorine as a prototypical example, we propose a first principle based device model that enables the prediction of channel orientation dependent high frequency performance of 2D transistor based integrated circuits by considering the inertia of the charge carriers. The prediction can be made solely from the knowledge of the 2D materials crystal structure, and thus it could be extremely useful for advanced technology research where experimental data is scarce. Since most of these materials inherit low carrier mobilities, our model can therefore help the circuit designer to extract the maximum operating frequency from a transistor, which is very crucial for 2D material based CMOS technology extension. On the other hand, the proposed model, which has been conceived as core in nature, facilitates the inclusion of various non-ideal and short channel effects using standard pre-correction techniques for further development of the full-fledged industry standard compact model as the technology matures. So in a nutshell, the flexibility and widespread applicability of the proposed modeling framework significantly upgrades the designer's toolbox for the exploration of 2D material based integrated circuits. Thank you.